Hello, hello, hello! Welcome back, everybody. It is Tuesday, the 20th of January, and today I'm going to be doing my first live solve of the summer cycle. So I've been spending obviously a lot of time going through the TMUA stuff and the ESAT stuff, but now that we're heading through towards A-level, which is our next big target, I want to make sure to demonstrate how my exam techniques can be applied to those papers as well. So I'm planning to do some of the A-level physics, some of the A-level math. Apologies for those of you who kind of regularly tune into my live streams that there was sort of no notice for this one. I was kind of working on the scheduling for this one. And I think from now on, the live solves will be on Monday mornings. I appreciate you guys will be in school, but when I'm doing the papers, it's much more me locked in with the paper anyway. So it's not too much of a big deal if there's not as much of a live audience. But I will still be carrying on with my evening live streams during the week. That way, like, more people can join in person, ask more questions, that kind of seminar series going through different techniques that you might have questions about. But today I thought I would do, it's going to be a bit sort of working out how this is going to work with the sort of live streaming. I've got A-level physics paper 2. The reason why I picked paper 2 is because from my tutoring the last few years, I know that paper 2 was just diabolical in some of the years. And so I want to like kind of go, okay, what did you guys go through? Put myself in your shoes and see how I would have handled the situation. Some says, how does one study when Cambridge Decision Day is in 8 days? You ignore it. There's nothing you can do about the Cambridge Decision Day. Honestly, I was like just wanting to do anything to focus on anything other than that. But I also appreciate that that's very tricky to do, because I also know a lot of people have got their like Oxford offers in already. And so to sit there and go, oh God, no, I just want it. But also what I think I would have done is I would have said, okay, let me assume I have the offer. My offer is conditional on me doing well in my A-levels. My A-levels are conditional on me doing well in this studying right now. I'm going to study like my life depends on it. So just reframe, refocus, like sort of like lightning going on a lightning rod, just find a new lightning rod and just go for that would be my advice to that. Cool. So I'm going to have a go at the paper 2, see how that goes. No, it's really frustrating because normally like you can download a paper and you can annotate on it. But when I downloaded this one, it's like some control settings, which means I can't annotate on it like directly, which is really frustrating because obviously like they've got the lines already there. So I thought it'd be really good to do that. Instead, I've just got the Miro whiteboard as an interim setup. I'm going to kind of work out the tech, which is my least favorite part of this gig, to sort of see if there's a better way of doing that. But for now, I think we'll just sort of have to make do the way we may do with the TMUA and the ESAT, with me just having the paper on the left, me writing on the right, kind of going down. Now, obviously as well, physics has much more of the writing in it. And so I'm thinking that's really boring. You just sitting here watching me just like write out sentences as paragraphs. So I think I'm going to go for much more of a, I will say out loud what I would have written out in full and just sort of bullet points on the Miro. And hopefully that should be fine. Cool. So let me get you guys moved over here. I've got the papers all lined up. Obviously, all rights to AQA for coming out with the paper. Now, I'll also put links in the description where you can find all the papers. So these are just the publicly available resources. 2 hours on the clock. I will time it, although I do not anticipate that I will need all of the time. So setting a timer, though, just in case. Now, what I'm going to actually, let me talk about what are the things I'm going to do. So in terms of exam technique for a paper like this, I will still be employing a bit of a multiple pass in that, so the first time through, I'll be answering the good questions. But if I'm getting too stuck in the mud, just to demonstrate good exam technique, I'm going to skip it immediately and try and remember to come back to it. Some of the things I'm going to do is mainly in the checking, actually. So in the paper, it's not going to be too much sort of extravagant, but really want to show you how I check my work in order to sort of maximize the marks. So I really go back over it, make full use of the time, add in as much detail as possible, check my answers a number of different ways. And that was the kind of belt and braces approach that I used to get my A stars at A level. So have a look out for that kind of technique. As always, drop any questions if you're live and you have any. I'll keep an eye on the chat just in case anyone is here and wants to ask anything. But in the meantime, I say, let's get going. So timer on the clock, 2 hours. Let us, ooh. That is a mark scheme. That is not a question paper. This is a question paper. 2 hours on the clock. Ready and begin. All right, so question 1. Let's name the topics as we see them. So this looks like thermal physics to me. Transferred at a constant rate of 35 watts. So state the melting temperature. Well, that will be here. That will be 28 degrees C. Just reading off from the graph because it melts at a constant temperature. So 1 mark for that. Explain how the energy transferred to the sample changes the arrangement of the atoms during TA to TB. TA to TB is during melting. So it's really asking for how the energy transfer changes the arrangement. So how does the energy transfer do anything? So question parsing, I have to talk about the energy transferred. So the energy transferred breaks the bonds. So I'm going to write that first. And it changes the arrangement of the atoms during the time interval. Well, the arrangement goes from ordered to disordered. It's still touching its nearest neighbors in a liquid, so I'm not going to put that down as a difference. But that's the main thing about the difference in the arrangement of the atoms when melting. And I might also add just for, free to move now. So they're no longer vibrating about a fixed position. I doubt that's going to be in the mark scheme. But with all of these, any wordy questions, I always put down more detail than is required just to make sure I actually get over the line. Oh, and God help them if they write an ambiguous question. Then I just like do a full data dump and say, here, find the mark somewhere in here and give it to me. State what happens to the potential energy of the atoms and to the kinetic energy of the atoms. Well, as you're melting, the potential energy increases. And the kinetic energy is staying the same because the kinetic energy is a measure of the temperature. So temperature is the average kinetic energy of the particles. It's melting at constant temperature, so kinetic energy stays the same. Describe how the motion changes from TB to TC. Well, that's increasing temperature. If you're increasing temperature, you're increasing kinetic energy, so they move faster. Will that be sufficient? I'll just add, because kinetic energy is increasing. That might be the sort of detail that kind of gets me over the line. Okay, so 1.5. Sample has this mass. I'll write down that information. Mass is 0.25 kilograms. Determine the specific heat capacity when in the liquid state. Right, well, I know that Q equals MC delta T. I remember, let's use the information from the full question. Because going back here, I remember there was a power is 35 watts. And where are we going? We're going when in the liquid state. So it's in the liquid state here. So that time, so I'm going to have to work, energy is power times time. I know this much. What time has increased? So that was 11.2. So the time is 14.8 minus 11.2, which is 3.6 minutes. So that means that energy is the power of 35 watts times 3.6 times 60, which, yes, I do have calculator. I didn't think it was worth getting an emulator because I think, you know what? I trust you guys. I trust you know how to press the buttons. So it's that many joules of energy has been given to the liquid in that time. Although I shouldn't have done that because I don't know the exact. Oh no, do I? Sorry, zooming in. I think it's safe to assume that is exactly 110. So in that time, the delta T is 110 minus 28, which I'm going to do on a calculator just because there's no point risking that. So 82 degrees C. So what that means then, putting this all together, is that 7560 is equal to M times C times 82. And then if we divide through, so C is going to be equal to 7560 all over 0.25 times 82, which is, please hold, for math. You're right about the timing not being the best when people are at school, but remember that when people are out of school, that's when I do my tutoring, like my full tutoring. So I'm very, very busy in the evenings. So I thought this would be a good time to stream, just put out a live solve because it's much more me with the paper. And that way people can catch up sort of on VOD in the comments there. People can ask questions. And it's kind of my way of sort of putting something out that people can consume in their own time. But you're right. It's definitely going to get a smaller live audience. So that's the number I get. And that is joules per kilogram per Kelvin. I think they would also have accepted per degree C there. Right, 1.6 now. Let me just make sure I'm kind of somewhat in line with what I've been doing, just so I don't go all over the place. So 1.6. Specific latent heats for fusion. M is known to be one of the elements. Identify it. So we have to work out the specific latent heat of fusion. So here, well, we know Q equals ML. So L is equal to Q over M. And we know that M is... have I thought of making like a community server, like a Discord where fans can join and just chill, discuss subjects? You're not the first one to ask that. I would need to think about how to do that. Because people do like chatting in the chat. But then I kind of like, especially when I know I'm dealing with a mostly sort of teen audience, then you get into sort of like, how are people, I don't know. I'm very safeguardy heavy and just sort of thinking about how to do all of this responsibly. I think I probably will at some point. I just need to investigate like how to do that. But it seems to be something that people are interested in. So thanks for asking. So here, I know the mass is 0.25. And I know the energy is power, which I said was 35, times the time during which it's melting. Let me just zoom in a bit as well, or just write bigger. Now, what is the time over which it's melting? So that is, so the time here is 11.2 minutes minus what is that? That is 4, 8, 1.2, 1.6, 1.8. So just taking the time to make sure I wasn't misreading anything on the axes there. So it's 9.4 minutes. So it's 9.4 times 60 up there. That's the number of seconds times the power. So that's the energy over 0.25. Satisfied with that. 35 times 9.4 times 60 all over 0.25 gives me 79.0 kilojoules per kilogram. Yes. Let me see if that was one of the options. 79, so gallium, let's call that 80. Also, if you have any ideas, if you're still here, yeah, if you have ideas about how you would use like a community server or a Discord or something, Do let me know, because I want to know what I'm missing out on, because I've never used it. So that, I think that's part of why I'm sort of like, ugh, it's because it seems unfamiliar to me. All right, so not 1.7, question 2 now. All right, so I'm seeing circular orbits. No, no. I will never get through a live solve without doing that. I swear to God. Right, so it shows a moon of mass M, circular orbit of R around a big planet of mass big M. Okay, so this is Kepler's third. This is just one of those things, you know it comes up and you just got to know how to do it. So here we know that this comes from F equals mv squared over r, where F is the force of gravity. So g m over r squared is, oh, let me have a, so I volunteered to mentor on one, and it's part of it is just people asking for help on questions they struggle on. Oh, okay. And the other part is people just talking with each other. That's interesting. And I suppose if it's all access to the public, everything is sort of out in the open. So, because the main thing you want to avoid is like adults talking to teenagers behind closed doors where there's not an adult consenting and all that kind of stuff. So if everything's kind of out in the open and anyone can join in, like there's nothing sort of, then that seems like something I can get on board with. That's really cool. So when you say you mentor on one, is that like you answering the questions that other people are struggling with? Do a bunch of other stuff like gaming servers and drop-ins. Unsurprisingly, the gaming server is probably not what I'm after, but I mean, people have asked me for one for like, for more when I'm going out live. Yeah. Okay. Right. So coming back to the question, I'll definitely have a think about that, because you're not the only one who's asked for a Discord server. So coming here, also just checking timing. Yeah, I'm fine. So the force of gravity, which is gmm over r squared, is equal to this mv squared over r. Little m's cancel. So we get that. Yeah, honestly, it would be useful because you could tell us in advance when you would stream. Yes. So my best way of doing that now is to try and populate them in advance, like on YouTube. But I get that people aren't always notified when I go live. So that sounds helpful. So thank you for that. Now, what I'm going to do here is to think about what in circular motion, what v is. V is equal to the distance traveled, which is 2 pi r all over big T. So if I square that up, I get 4 pi squared r squared over t squared. Now, plugging that in for v squared here, we're going to have that gm over r squared equals this guy divided by r. So it's just going to be a single r on top. And if I rearrange this to make t squared the subject, I get that t squared equals 4 pi squared r cubed over gm. And therefore, k is equal to 4 pi squared over gm. Okay. Don't have much experience modding, but wouldn't mind helping setting one up. I'll definitely have a think about this, because it definitely, like, it is. Thank you for that. People have been asking, and so to know kind of what it is, maybe I should join one, get a sense of how they're used. But if you think, and a bunch of other people think it's a good idea, and I can do it responsibly, then yeah, absolutely. 2.2. Data for 2 of the moons of the planet Uranus. So, okay, so what this is saying. So what we know here is that t squared is proportional to r cubed. So in other words, coming from here, that's to deal with the proportionality, what that means is t squared over r cubed is a constant. Okay. And that's what we're going to use here. So what that means is T1 squared over R1 cubed equals T2 squared over R2 cubed. So it means that 1.41 squared over 1.29 times 10 to the 8 cubed is, and it doesn't matter that the unit is days because here it will cancel, equals that squared over R cubed. And let's rearrange for R cubed. So it's going to be 4.14 squared times 1.29 times 10 to the 8 cubed, all over 1.41 squared. I'll seen that there's another comment, so I'll come back to it once I've submitted this. Times 1.28 10 to the 8 cubed, all over 1.41 squared. So it is, this value is 1.81 times 10 to the 25, but I have to remember to cube root it. And when I do that, I get an answer of 2.62 times 10 to the 8 meters. Okay. Someone's saying it could be centered on something like ESAT. You were in a Team UA group, I think GC stands for group chat this year, and I'm not sure how much it helped, but it definitely made me feel like I wasn't alone because TMUA is nasty. And as long as you aren't currently working in a school, which is correct, there shouldn't be safeguarding issues. You say that. It would be aimed at, I guess, 16 to 18-year-olds unless you choose to expand to other years. I would not do that specifically because I just like working with teenagers anyway. A-level is like my bread and butter. Love it. But it's more because I've been working with kids in some capacity since I was 13. And so I'm just like hammered, safeguarding. And so I just like very much like to be very, very careful because I am not about to turn out to be the Colleen Ballinger of education. Safeguarding matters, even if it's not a sort of legal requirement. So I am sort of cautiously overprotective. And then I sort of go, and then everyone's like, dude, calm down. And then I'm like, okay, yeah, you're right. Okay, so now calculating the mass of Uranus. Well, that, yeah. So what we have to do here is to work out what K is, because if we work out K, then we can rearrange it for M. So 2.3. So what we've got here is K is 4 pi squared over GM, which means that M is equal to 4 pi squared over G times K. Now, K, remember, is that constant T squared over R cubed, which I should have worked out in 2.2 and didn't, because that's helpful. Right, so what I'm going to do is just recalculate what that should have been. So that is, this guy here on the left is K. So this 1.4, although now I am actually going to have to be careful because that is in days, and now the units do matter because the time period should be in seconds. So that's one thing in physics, constantly thinking about units. So what I'm going to have, okay, I will rewrite this now. So K is equal to T squared over R cubed. So here, T squared, let's do it for Miranda because we have everything precisely. So it's 1.41 days, 24 hours in a day, 3,600 seconds in an hour because I'm cool and go straight there. So T squared over R cubed gets me a value of K of 1.41 times 24 times 3,600. You square it. All over 1.29 times 10 to the 8 all cubed. So I get the K is equal to 6.913, too many sig figs, whatever, it doesn't matter, times 10 to the minus 15, whatever the useless units are. Well, that's seconds per meter, seconds squared per meter cubed. That's irrelevant. But the point here is now that I have K, I can put that in, find the mass, because mass is going to be equal to 4 pi squared all over. No! Where's my formula book? God damn it. Where's my constants? All right, so AQA, that's the one thing I forgot to do before stream started, and I was really hoping I could get away with it. And of course, the answer is no. A-level physics formula sheet. Now, as penance, I will have to do my best guess as to what I think it is. I think it's 6.67 times 10 to the minus 11. Let's find out. Boom, nailed it. 6.67 times 10 to the minus 11. Okay, that's big G. 6, let me also check to make sure you can see, because I don't think you can anymore. Cool. 6.67 times 10 to the minus 11 times 6.9135 times 10 to the minus something something. 15. That's going to be a big old mass. All right, so 4 pi squared over 6.67 10 to the minus 11 times answer is 8.56 times 10 to the 25 kilograms is the mass of Uranus. Great. Okay, so we're talking about escape velocity in 2.4. God, it's been a while since I've done escape velocity. Let me remember this. So I know that it's the gravitational potential energy. So it's you need as much kinetic energy as the potential energy in order to escape the orbit. Potential energy is gm over r. So in terms of the actual potential, though, that would have to equal half mv squared. So the m's would cancel. And so the escape velocity would be root of 2gm over r. So what we're looking for the greatest escape velocity is the biggest value of big M over diameter over r. Hi, do you do IB questions? Yes. However, the IB is like, again, what we were talking about with me, like just sort of wanting to be really, really, really cautious about like setting up a Discord. I also want to be really, really, really cautious about upsetting people with like copyright and stuff. And IB, these guys, they're like, yeah, have my papers. Do what you want with my papers. And then IB's like, do not touch me. Get off. You can find my papers nowhere. We're coming for you. And so I'm like, I don't know if I want to mess with that. So, but also obviously I'm very small and so no one knows I exist yet. So maybe because I really want to do math paper 3. AAHL math paper 3 is insane. So what it may be is POV 337 people. Yeah, I mean, we're getting an insight into my psychology here, guys. No, but I'm thinking what I could do is I could do a bit of IB, but like unlist it maybe, and then get like some links if people want it. Maybe that could be helpful as part of a Discord server. I could, yeah, I don't know. I'm still working out sort of exactly how I want this to look and how not to make the YouTube gods angry and try to get to as many people as possible. I think in terms of IB, if you want the physics is very similar because this also has long form stuff. This also has multiple choice. There are some topics that are in the IB that are not in the A level, like the greenhouse effect, which are more IB specific. So it wouldn't be with those. But in terms of exam technique, a lot of the stuff that I'm doing is going to be broadly transferable. So here, what we want is to work out the largest value of big M over little r. So I'm just going to work out. Oh, did you see the news that they're getting rid of Matt and Pat? No, I did not. You're breaking that here. Getting rid of I'm so happy they're getting rid of the PAT test because they wrecked it. They absolutely ruined it last year when they moved to the online system. They're using ESAT and TMUA now. I'm so happy. Although, rip the Matt paper. Matt was so much fun. It makes sense, but like, which means more hadn't even thought of it from that perspective. Which are more attraction to the channel next year. Yes, guys, let's go. I was genuinely thinking about it from your guys' perspective first, because the PAT, they changed. Okay. It was so annoying, guys, because with calm, focus, explain. PAT test, it used to be long form written. They changed it to an online format, which was multiple choice only, but decided to like just not really give you any proper practice papers on the brand new format, and then just never released any past papers once they even started doing it. So everyone was going in completely blind. Absolute nonsense, absolute madness. Thank God for the end of that, because I've had some really top tier candidates get tripped up by that. And so, yeah, I just feel badly for them that they didn't apply next year. The math multiple choice were really fun. Yeah, honestly, at least we still have the math. We had the good days. Now we can just do the math for fun. Right, so let's go over here. Let's work out what the values of big M over R are. And in fact, if that's the diameter, it's just whatever. It's that over 2. It's still the point. I'm just going to divide these and see which one's biggest. So for aerial, honestly, like, you know what I'm doing. I'm putting the mass over the diameter and seeing which one comes out on top. So top one is 1.09 times 10 to the 15. Then we've got 3.03 10 to the 21, all over 1.52 10 to the 6. So that's 1.99 times 10 to the 15. And then we've got 3.49 times 10 to the 21, all over 1.58 times 10 to the 6. So we get 2.21. And ding, 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 we have a winner. It's titanium. Yeah, but home students. True. True. The IB home students are going to get trashed by international students. Home scores are dropping. I have some opinions on. I'll see. I'll see about how to do this, because I think, especially when it comes to like math paper 3 or like physics paper 1, like, I've got some opinions on how to demonstrate exam technique. And I think let's bear in mind as well, let's be honest about the fact that a lot of this stuff you can just find online. And if you're looking for answers, those can be found. I think what I do well is like demonstrate the exam technique, really put myself in your position, put together a full run. I mean, granted, in a full A-level physics, you're not going to be stopping to chat the whole time. And my timing is probably out the window, but exam technique. Spring mechanism can project an object vertically to a maximum height of 1 meter from the surface of the Earth. Oh, okay. Right, so what that means in a spring mechanism is that the potential energy is getting turned into GPE. So let's work out what the and so it has that much potential energy. Let's work out what that potential energy is. Well, it would be M, which we don't know, times G is 9.81 times delta H is that. Well, we have to work out what little g is on aerial. And little g, so we just have to, little g is, well, let me start. I like doing things from first principles. GM over R, GMM over R squared. So this becomes little g. So let's work out what that is on aerial. So on aerial, we've got 6.67 times 10 to the minus 11 times the mass of 1.2 times 10, 20 stuff, all over the radius, which I have to remember to divide by 2 this time. Now it does matter. 1.16 times 10 to the 6 divided by 2 is 5.8 times 10 to the 5 squared. And if I run all of that, see, top tier content, you guys watching me type stuff into a calculator. I mean, I could get like an emulator that would display on the screen, but bleh. So G there is 0.252. Which means that the GPE, when raising that to a height of 100 meters, would be m times 0.252 times 100. So that's obviously equal to 9.81 m. And this is 25.2 m. So that is clearly more energy required than what was given to it. So it does not make it. Need more energy does not make it. Yes, this is physics. I'm also going to do some A-level math, but I just thought I'd start with physics because I feel like, especially with a lot of my biggest stuff was like the Cambridge Science interview stuff and like the ESAT stuff, and so I thought people would like me to start on the physics. Question 3. Masses of ions. Okay, so yeah, this is a classic. We have an electric field, we have a magnetic field. That's creating an electric force and a sort of magnetic force on the charged particle of positive lithium ions. Okay. Most ions are deflected. One particular speed, moves at speed v. Draw 2 labeled arrows showing the direction of the electric force and the magnetic force acting on A. Okay, so what we know is the electric field lines show the direction of a positive test charge. These are positive lithium ions. And so God damn it. So the electric force goes down and the magnetic force goes up. And the reason why the magnetic forces goes up, left-hand rule. So you've got your I'm not even going to tell you how my cousin. Actually, maybe I will. Well, so the M for motion, F for field, C for current. So it was MFC. And how my cousin remembered it, I'm not able to tell you, but I remember the first word was mother, and I'll let you extrapolate. And it means I always tell my students this because it means they never, ever forget the orientation. So the field is going into the page. The current is going right because it's the flow of positive charge. So the magnetic force is acting up. Okay, so that's that. 3.2. Lithium ions traveling at that speed pass through the small aperture. Calculate E. Well, it passes through the aperture when the magnetic force equals the electric force. Or rather, I'll write them the other way around just because we want E, and so it's just easier if that's already on the left. So it's when the electric force equals the magnetic force. And the electric force is E times Q, and the magnetic force is BQV. Those obviously cancel. All right, that's really simple. Great, love to see it. So that means that E is equal to 0.12 times 1.5 times 10 to the 5. 5. Running that, we get 0.12 times 1.5 times 10 to the 5, which gives us 18,000 volts per meter. Sweet. Okay, so 3.3. How am I on time? Fine. Ions pass through the small aperture, enter a second uniform magnetic field, and then curve round. Different masses are separated because they follow different paths. Okay. Show that that is that. Well, we again know that F equals mv squared over r, where the force here is the magnetic force of BQV. And let's rearrange for r equals mv squared over BQV, where then the v's will cancel, and you just get that it equals mv over BQ as required. Okay, good. So 3.4. The ions of different mass are deflected and strike the detector surface at different distances. Singly charged ion passes through the aperture. Calculate the distance between the aperture and the point where this ion strikes the detector. Well, what we know, that's the radius of curvature. So that distance, I'm just going to clock this, is going to be 2r. Is what we need to calculate. So therefore, we need to calculate 2mv over bq. Come on, you can do it. Over bq. And we need to do it for these things. So it's 2 times mass times v over b times charge is going to be 1.6 times 10 to the minus 19 because it is singly charged. And again, running all that. And one thing I really like about having a live chat while I do this is because it means that like you guys can bring things to me that I haven't considered yet and like kind of give me advice on how to build this thing out and what would be useful for you. So I kind of like that you can kind of drop in and be like, give me a Discord. And I'm like, instant feedback. Love it. That's too big. But that's too big, though. There's no way it's 156 meters. I've done something wrong. What have I done wrong? R is mv over bq. M. There we go. I typed into 23 on the calculator. So it actually, there we go. That's much more. Now look at what I just did there, because this is an important moment. I sense checked my answer. I didn't just assume that because my calculator spat it out that it was correct. I kind of went, does that make sense? The answer was hell no. So I knew I'd done something wrong, and that's how I knew to go looking for that execution error. Very helpful exam technique, that. Okay, so 3.5. Different type of mass spec. So what happens is the ions are going through that gap. Okay, so what we've got here. Do I know my E-fields? How well do I know my E-fields? So it's at the midpoint between the parallel electrodes. I think the midpoint there is going to be at 3,000 volts. So this is parallel plates. So E is equal to V over D. And V is equal to E times D. But the idea here is E is constant. So if the distance between the full plates is the full 6,000 volts, then half the distance will give you half the voltage. So it is definitely accelerated through 3,000 volts. And I know that work done, so that voltage is work done per unit charge. So if I multiply that by the charge of 1.6 times 10 to the minus 19, I will get the electric energy sort of given to that. And I know that that energy will be transferred to kinetic energy. So there's 4.8 times 10 to the minus 16 joules of kinetic energy. And then what that means is 4.8 times 10 to the minus 16 will equal half m times v squared. So if I do that over 0.6 times 10 to the minus 26, I get that v squared is equal to 8 times 10 to the 10, which means that v is the root of that, which is 2.8 times 10 to the 5. Yeah. So that should be the speed coming out, 3.6. I'm kind of bored now, and I want to just get to the multiple choice. You see, ESAT was just much more fun in comparison. So these ions are produced in the sample simultaneously and travel a distance L from aperture P to the detector. Okay. So these two different isotopes are produced. For each type of ion, the time interval is measured. Discuss how the masses can be deduced from these measurements. Well, as we've established here, the charge is the same, the voltage is the same, so the energy given to them is constant. But if kinetic energy is a half mv squared, and kinetic energy is a constant, then v squared is equal to 2 ek over m. So and v is equal to, does it give us an L? Distance L. So v is equal to L over t. How the mass can be produced. Now let's rearrange this for m. We say m is equal to 2 times the kinetic energy, which is what we calculated before. It's the 4.8. I suppose it's asking for discuss, though. VQ. All right, I feel like I'm straying from what the mark scheme wants, but just roll with it for a second. T squared over L squared. In other words, the mass is proportional to T squared. So by measuring T, we can plug it into this equation and work out what the mass is. To be honest, you can go on the... True! There just aren't enough questions. I haven't done all of them. I think I've done all of them but the 2016 or 2017. But there's also, like, because what I do is much more about the exam technique anyway, there's always a chance I just redo them, because I didn't get full marks in all of those early ones, because, I don't know, baby streamer was nervous about streaming, and so I was like, and, like, freaked myself out and got stuff wrong that I should not have got wrong. And to be honest, I'm just not, like... there's already an R2 Drew 2 for the TMUA, and his scores are better than my scores, so I'm really happy to just, like, give the TMUA to him, because I just hate paper 2, but god damn it, I love the ESAT. So 4.1, calculate the RMS voltage. RMS voltage, VRMS, is peak over root 2. So 15 over root 2 is 10.6 volts. Great, no challenge there. Determine the Y volt. No, don't make me do Y gain. No, why? Okay. Oh no, so let's look at the units. It says voltage per division. Let's work out what the voltage is. So the peak we know is 15. So we know that is, so it's 4.2. There are 3 divisions. So 15 volts over 3 divisions is very simply 5 volts per division. DC supply gives the same rate of energy dissipation in R as the AC supply. So that is power. So the power is the same in R. Where is R? Okay, so power supply going to R. Okay, so the power in R is the same. Draw the trace of the output of the DC supply on figure 7. That's figure 8. That's figure 7. A DC supply, what would the DC supply be? Well, that would be the RMS, so that would be 10 point whatever I said. So it would be a constant 10.6. Okay, and if that's 15, that's 10. 1, 2, 3, 4, 5. So each single division is 1. So it'd be a kind of a straight line. I can't draw it on, but like, just trust me, bro. I did this. It's close to 11, so it's sort of just drawing a straight line on constant voltage at that sort of 10.6 level. Straight. I'll just write down what I would have done. So straight line at 10.6. 4.4. These questions are just unfun. Maybe I should, yeah, I'll get to the harder paper twos. Like the brutal ones were 2022 and 2023 from my understanding. Square wave generator between 0 and 15. Trace of the new waveform. Time base is set to that. Calculate the frequency. Well, the frequency is, let's work out the time. So frequency we know is 1 over time period. The time period is when you get to equivalent points. So let's take these points because that's when they kind of shoot up. So that's 1, 2, 3, 4, 5, 6, 7, 8 divisions. So it's 8 times 5 times 10 to the minus 4 is the, nope. I assure you guys I'm literate. I should really get some shortcuts on this little pen. I'm sure that would be helpful. Now, the frequency is 1 over 8 times 5 times 10 to the minus 4. I also like that I don't hide from you guys when I absolutely hate a question, because these are all the comments that go through your head when you're doing a paper as well, and that's what goes through mine too. 4.5 shows the arrangement of a square wave generator. Capacitor, interesting. Deduce the time constant. Well, we know the time constant is the time taken to go to 1 over E, which I think is 37%. Let me just check that. E to the minus 1. So we want it to get to about 36.8% of its initial value. So if you start at 15, which is the sort of, so 15 times that. So we're looking for where it gets to about 5.5 volts. Now looking on here, that would be, so each of these we said was 1. So that's 5. 5.5 is about there. And tracking that down, that's about here. Now, question 4.4, the time base. So it was about 4/5 of the 1 division, which was 5 times 10 to the minus 4 seconds. So I think it's 4 times 10 to the minus 4 seconds is the time constant, is what I'm going with. State and explain. So we're getting into the wordy parts of the paper again. So 4.6. State and explain a change to one control setting on the oscilloscope that would reduce the uncertainty in the value of the time constant. We could control, it's either, we could either control the Y gain, which would reduce the uncertainty in the Y value, or we could increase the time gain. That was what it was called. So I clearly need to review oscilloscopes. The time base. Let's go for that. Let's go for increase the time base. Or rather, decrease the time base. Yeah, so decrease the time base. So I'm going to say that. I'm going to say less time per division. And so I'm going to say, so therefore there's less uncertainty in the time measured. I'm thinking, could they want something else? So if you're reducing the time base, so there's less time per division, I might say more divisions, therefore less uncertainty in time measured. Something like that. That feels, and again, I hate the wordy questions. It's one of the reasons I kind of want to gravitate to the math more than the physics, because like with the words, you can speak around the marks, but not get the marks, and it's just not fun. But that's an important part of the process. And so I don't mind getting egg on my face to kind of help you guys work your way around that. So 5.1, how am I doing on time? Yeah, fine, about still less than an hour in. State the fundamental force involved when alpha particle 1 is scattered by the nucleus. That is electrostatic. Uh, 5.2. Draw an arrow at position X to show the direction of the rate of change of momentum. Rate of change of momentum is resultant force. So that will be aligned from the center of the gold nucleus. So in other words, if that's the nucleus and that's X, you want to draw a line from the center of the nucleus straight through and kind of in that direction. Suggest one of the alpha particles in figure 11, which may be deflected downwards with a scattering angle of exactly 90 degrees. I think 6 overshoots the mark. I think it's going to be 5. You got to hit it, but not like hit it. And we know that force is going to go bounce back. So I'm going to go with 5. I'm going to say it's 5. Justify your answer. Well, I did. Don't make me. But you can see that's kind of, I understand it, but how do I explain that? 90 degrees. It hits it. So I'll say hits nucleus not dead on. I'm also going to be like sort of belt and braces here. Well, that should really be head on, like a head on collision. And what I would do in the exam is I would really explain it. So I would also explain why it couldn't be the alternatives. 4 would bounce back bigger. So, and I will also then say 4 would be bigger than 90 degrees. Nope. So 4 would be bigger than 90 degrees. And I think that 6 would be less than 90 degrees. So I think 5 is the one that has to be 90 degrees. And that's what I'm going to go with. 5.4. Alpha particle 4 comes to rest at that distance from the center of the nucleus. So distance of closest approach. Okay, so what we're talking about here is kinetic energy turning into electric potential energy. So the half mv squared turns into kq1 q2 over r. Those were meant to be on the bottom. So kq1 q2 over r, where k is 1 over 4 pi epsilon naught. And you can tell I've been doing too much IB because I called it k. Let me go to here. Do they accept k? Were they actually making you do it? I think they're actually, yeah, no, yeah, okay, so okay, fine. 1 over 4 pi epsilon naught. No. Okay, so 4 pi epsilon naught r, because that's the potential, electric potential energy. Cool. So calculate the speed when it is at a large distance. So we want to do solve for v. So v squared is, nope. Come on, I can do this. 2 Q1, Q2 over 4 pi epsilon naught m r cancels down for 2. So V is the root of alpha has a charge of 2 times 1.6 times 10 to the minus 19. Gold has 79 protons, so it has a charge of 79 times 1.6 times 10 to the minus 19, all over 2 times pi times epsilon naught is 8.85 times 10 to the minus 12 the alpha, which is 6.8 times 10 to the minus 27 times the distance of closest approach, which is 5.5 times 10 to the minus 14. Don't you love the calculations you get in A-level physics? Right. Let me work that out. Now, I realistically, in terms of exam technique, should probably not have done this all in one go like this. Just because if I get this calculation wrong now, I won't pick up method marks for it. So I probably should have done it bit by bit. But we're here now. 6.8 times 10 to the minus 27 was the mass, times 5.5, 10 to the minus 14 is... Let me scroll back in so we're at full size. So I run that and I get 1.4 times 10 to the 7 meters per second, keeping the same number of significant figures. So I'm happy to lock that in. 5.5. Nuclear radius is that. Calculate the nuclear radius of that. No, don't want to. No, okay, I do know what this is coming from. This is coming from the idea that all nuclei have the same density. So the radius is proportional to the cube root of the mass. It's been a while since I've covered this part of the syllabus. Okay, because I haven't covered this part of the syllabus, I'm going to have to derive it from first principles. I do know that the point of this part of the syllabus is that the density of a nucleus is constant. So let's say I've forgotten this. Let me show you how I'd still get there. So if density is constant, that means that mass is equal to density times volume. So the mass is equal to the density times 4/3 pi r cubed. So it means that mass over r cubed is equal to 4/3 pi rho, which is a constant. So what that means is that m1 over r1 cubed equals m2 over r2 cubed. So r2 cubed equals r1 cubed times m2 over m1. Or in other words, R2 is equal to R1 times the cube root of M2 over M1. So that's me deriving things from first principles, which means it's going to be 6.98 times 10 to the minus 15 times the cube root of 107 all over 197. Which when I run that will give me an answer of, wait for it, 107 over 197 is 5, let me make sure it's the same number of significant figures, 5.70 times 10 to the minus 15. Not 100% confident, it's been a while. if you think about it, the mass, it's good that it is in U, but the U is going to be on the top and the bottom, so it's going to cancel. So in theory, it should be in kilograms, but the conversions would cancel anyway, so I'm going to run with it. But you're right to constantly be keeping an eye on units. 5.6. OCRA, it's entirely possible it's not in your spec. The reason why you could see me kind of umming and ahhing, I think it's quite a niche part of the AQA syllabus. So this is very much an AQA paper. Results may vary on like whether like the niche parts of different syllabus. So if you haven't seen, also you may just not have learned it yet. This is a full A-level paper. You guys are in January, so there's some things you may not have covered. 5.6, right. This is exactly what I used to solve for 5.5. State one conclusion about the nucleons in a nucleus that can be deduced from this fact. Well, the reason why this matters is if you think about it, a hydrogen atom is just a proton, but then as you move up the periodic table, there are more and more neutrons in a nucleus as compared to protons. You're retaking, so hopefully you've seen everything. All right, let's just say that it's not the OCR syllabus then. Because yeah, I got people, there are all sorts of like syllabuses. I've got a guy who's doing what's it, the CIE A-level for chemistry and for physics, which is brutal because you have like 5 or 6 papers for those. And this is why you've got to like really get deep in your syllabus and know the niche parts of all the different curricula. So that's why I was like, oh, I know for IB you have greenhouse effect in a way that you don't have in other syllabuses. Just making sure you kind of go line by line on your spec and make sure you know all of it. So time-wise, only an hour in. I've still got plenty of time. So one conclusion about the nucleons in a nucleus would be that protons and neutrons have the same density. But again, this is a part of the spec I haven't revised. And that's what you, by the way, this is me showing you, I have good general physics knowledge, but to like 100% a paper, you've got to be so deep on the specific knowledge of your specific syllabus. I'm going to go for that. CIA paper 1 can be good prep for ESAT though. So many multiple choice. That is good to know. Because what I can do, I've got plans for the summer, guys. I've got plans for how to develop your speed. So I really want to do like GCSE math papers, but like challenge papers. So because GCSE math is so similar to ESAT math 1, that's a good way to work your speed test. So I want to do like speed runs of that. And I want to do challenge runs where I do the entire thing like mental with my hands on my head, like full mental math, like make it as hard as possible, as quick as possible. Like that's going to be really fun this summer. But it's good to know that there are other resources I can use to prep for the ESAT now that I've burned through pretty much all the papers. There's like 4,000 plus multiple choice questions. Damn. I mean, that's good because it's free. I know there are things like ESAT Ninja, but those are behind a paywall, so I'm obviously not going to stream that. But like anything I can do to sort of demonstrate how to practice those multiple choice is super helpful. So thank you for that. Thermal nuclear reactor. What guys? Like, how long is this paper? I'm bored. It's not ESAT. It's not interesting. No, it is interesting because getting marks is good. This is fuel in which the ratio has been artificially increased. Describe what happens when the neutrons interact with this in a thermal. I could keep getting free trials, but that doesn't mean I can stream the free trials because those questions are still behind a paywall and I want to respect their copyright. I'm not about to be messing up other people in the game. We all got to make our living. I will say about ESAT Ninja that some of the questions were just not great in terms of the questions were either just wrong or some of them required calculator, which is obviously not right. So I'm going to say uranium-238, nothing happens. or I might say deflect. In a thermonuclear reactor, U235 absorb and cause fission. But I will also say only if thermal, only if slow enough. And maybe I'll also add for uranium-235 that if they're too fast, they deflect. Because it's hard to know exactly what they're going for, which is why you play the game of really going through the mark scheme analysis. Okay. So 6.2. You're saying you did the chem section last year and it spoke about Zwitter ions, which just weren't in the spec at all. Damn. Yeah, I don't like the CIE. Show that the mass of uranium-238 in this sample at that time. Okay. Okay, so what we've got here is m equals m naught e to the minus lambda t. We're told the decay constant. We're told the time. We want to solve for m naught. So m naught is going to be equal to 9. Well, I'll call it 0.993 to keep it in kilograms like we want. All over e to the minus 1.54 times 10 to the minus 10 times 2 times 10 to the 9. And if I run that, I get e to the minus 1.54 10 to the minus 10 times 2 times 10 to the 9. So I get 1.35 kilograms, which is approximately equal to 1.4 kilograms for 6.2. 6.3. Thermonuclear reactor requires a minimum of 3% of its uranium mass to be uranium-235. The ratio has changed over time. Okay, so that long ago, the sample contained 52 grams. Well, I know, so 52 grams. Well, we know that it was initially, okay, let me, because this is just, okay. What we know is the uranium-235 is 52 grams back then. The uranium-238 was 1,350 grams back then. So 52 all over the total mass of uranium times 100. 50 times plus 52 on the bottom times 100 is 3.7%. And so the answer is yes. End of section A. Yay! Okay, multiple choice now. No, this is ESAT Ninja. Oh, sorry, I completely misunderstood what you were saying. Yeah, Zwitter ions in the ESAT Ninja. Yeah, you get some rogue stuff. So, but I mean, they have loads of questions. So a lot of the ESAT Ninja stuff is good. but it's just some of it isn't. Knowing to parse them out is a challenge at times. Okay. Let me zoom in a bit more. So when an ideal gas at a temperature of 27 degrees C is suddenly compressed to 1... Okay, so this is PV equals nRT, and I'm going to call this a before and after. So I use this a lot with my people doing IB paper 1, is considering a before and after. So what I do is I write the equation for the second case. The number of moles is the same. And then I rewrite this in terms of the first quantities. So it's compressed. So the pressure increases by a factor of 7. So P2 is 7P1. When the volume is a quarter of its initial volume, so that becomes a quarter of V1, that's equal to nRT2. So 7 over 4 P1 V1 equals nRT2. And we know that P1 V1 equals nRT1. So dividing through top equation by bottom equation, we get 7 over 4 equals T2 over T1. Very simply from that. Which means that T2 is 7 over 4 T1. And remembering to convert to Kelvin, that's 300 Kelvin. So it's 7 over 4 times 300, which is 525 Kelvin minus 273, which is 252 degrees C, which is D. Would it be easier to do PV over T equals K? It's kind of what I did, in a way. It's just I divided it through separately. Let me show you what that would have looked like if you'd done that. So if you'd said that PV over T is constant, that means that, well, it means that P1 V1 over T1 equals P2 V2 over T2, which would, and P2 is, and again, so that's 7 P1 times a quarter V2 all over T2, which ends up being the same, just in different order. So cancel, cancel, cancel. And T2 is once again 7 over 4 T1. I like the before and after. Although it is a bit longer, I find it helps with people who don't have like the deepest understanding of physics, to sort of brute force your way through it. Just sort of writing up the equation on one line 2 times and dividing through. It's when you don't get a sense of proportionality, it sort of cancels it for you. It means you have to think about it less. I hate questions like this. Okay, so question 8. 2 flasks connected by a thin tube of negligible volume. Ideal gas. Volume is twice that. Temperatures are like that. There's no net transfer, which means the pressures are equal. But the number of moles will not be the same, will it? No, but that's the point, is the mass. So the mass is proportional to the number of moles. So if we can get the mole, okay, so P is constant, so I won't give it a subscript. So PVX equals NX RTX, and PVY equals NYRTY. And what I really should have done, let me just fill in what I know. Or, hold on a minute. So X is twice the volume. Okay, so let me fill that in what I know here. So that's P. Vx is 2Vy. And Tx is a quarter of Ty. And we know that PVy equals NYRTY. And again, if we divide the two equations now, we're left with 2 there, because the p's cancel, the vy's cancel. So 2 equals nx over ny. R's cancel, ty's cancel, times a quarter. So 8 equals nx over ny. So the number of moles of y is nx over 8. And mass is equal to moles times molar mass. So that should just be the mass ratio should be the same as the mole ratio. So it should be m over 8, which I'm going to say is equal to A. 45 minutes left. I'm doing plenty good on time. They cannot give up on ideal gases, can they? 1 mole at a temperature of T. Second sample of an ideal gas is 2/3 of a mole at temperature 2T. The total molecular kinetic energy. Oh, I don't like that. Let me go to my formula sheet. Thermal physics. So I know that the average kinetic energy of a particle is 3 over 2 kT. And then I know that the total would be 3 over 2 kT times the number of particles. And I also know that the number of particles is the number of moles times Avogadro's constant. So in other words, the total energy is proportional to the product of NT. So let's define this for P. So for P, the energy is E, is 3 over 2K times T, N is 1 times NA. That's what E is. So for Q, let's call that EQ. That is 3 over 2K. The temperature is 2T. The number of moles is 2/3 Na. So cancels is equal to, well, in fact, let's not do that. Let's not do that. Because this is equal to 3 over 2 KTNA into 2 times 2/3. So it's 4/3 E, which is C. They are not letting go of the ideal gases. Ideal gas is contained in a cubical box. Gas has N molecules, each of mass M. What is the pressure exerted? Again, I'm going to go back to my formula book, because I've got this kinetic theory which says that PV equals 1/3 NM CRMS squared. I think, so the volume is A cubed. What is the pressure? So the pressure is NM over 3A cubed CRMS squared. I'm really hoping that exists. It does. Great. That is D. 11. An experiment where Brownian motion is demonstrated using smoke particles in air. The experiment makes it possible to see the motion of... No, you don't see the motion of air molecules, but you do see the effect. No, it's the collision of air molecules with smoke. Yes, so it's C. 11 is C. So the air molecules collide with the smoke particles and cause them to move around. So that is that one. This is 12. Let me zoom out so we can see the question. Graph shows how the GPE varies with vertical distance d from the surface of the Earth. What does the gradient represent? The negative, or the G field is the negative of the negative potential gradient. So the gradient of V over d, it should be the magnitude of the gravitational field strength, which is d. 13. What is the angular speed of a satellite in a geostationary orbit? So angular speed is the angle moves is 2 pi over t. And we know in geostationary orbits, the time period is 1 day. So it's 2 pi over a day, which is 24 hours times 3,600 seconds in an hour, which when I run that through gives me a value of 7.3 times 10 to the minus 5, which is B. Nice. So 14. Two fixed charges repel each other with a force F. So F equals, I'll call it K this time, Q1, Q2 over R squared. So now, if this is given to that, the new forces will be K. This will now be minus Q. This will now be plus Q over R squared. So that's minus a third of F. So it will have a magnitude of F over 3, and it will now be attractive because it's negative, which is D. Let me just check I haven't done anything silly there. Don't think I have. Okay. Cool. Question 15. And again, it's just keeping the stamina, making sure I'm doing well moving through the run with plenty of time left to check the work at the end. A distance L from a fixed point charge. The electric field is E and the electric potential is V. Electric field strength and electric potential at a distance of 3L. Well, field strength is proportional to 1 over R squared, and potential is proportional to 1 over R. So as I triple the distance, E will go to E over 9, and V will go to V over 3, which is C. So just from understanding that proportionality. 16. Of equal potential difference near an isolated point charge. Okay, so an isolated point charge we know will have a radial field, so it's not going to be A or B. It's going to be C or D. And we know, like I said before, that the potential is proportional to 1 over R. So if we think about what that means, that kind of 1 over R graph, or we've even seen the graph earlier. So in terms of exam technique, let me show you. So this is the V over R graph. We can see if we draw on lines of similar vertical spacing, we can see for each given vertical jump, the distance you have to move across is increasing. In other words, the distance between the equipotential lines will be increasing, and that will give us an answer of D. Can we think of it like a magnet where spacing gets further each time? Honestly, any way you can think of it that gets you there will work. Um, because yeah, there's a lot of similarity between the way these fields operate. In my head, I don't go to magnetic fields there, but that doesn't mean it's not right. 17. Positive charge is placed in an electric field at a point where the potential is that. What is the potential energy? Well, potential energy is just joules. That's energy per unit charge. So we multiply those together. We get 500 times 2 10 to the minus 4 would be 0.1 joules, which is A. I'm just going to run with that. And the reason why that is because voltage is work done per unit charge. So work done is voltage times charge, making sure there's something visual for the visual people out there, which is 1 times 10 to the minus 1. Cool. Moving on to 18. Two-point charges are that far apart. X is on a point. X is a point on the line between them where the potential is 0. This is more interesting. I'm going to focus now. Where the electric potential is 0. So remember, the potential is KQ over R from a point. So at this point, so I'm going to redraw this just so we have something. So we're going to say there's a point here where this is X, which means this is going to be 0.1 minus X. Actually, I'll just, this will work if I keep it in millimeters, I think. Because it would be the exact same thing if I worked in, no, I'll be consistent. I'll be good. No shortcuts, 0.1 minus X. So that's 2 microcoulombs. This is minus 3 microcoulombs. So at this point, X, we know that the potential is and this time I will, K times 2 over X minus 3K over 0.1 minus X equals 0. Yeah, the answer is in millimeters too. I kind of agree, but yeah, go on. Let's define it all in millimeters. Maybe I can run it both ways and show that it works both ways. But I think some people really prefer working in base units the entire way through a run, just to remind yourself, like, constantly look at the units, because that can be a trap elsewhere. So what that means is that 2K over X equals 3K over 100 minus X, which means that 100 minus X equals 1.5X, just by rearranging. Actually, no, I won't skip steps. Equals over 2K, where those cancel and this becomes 1.5, which is why 100 minus X is equal to 1.5X, which means that 100 is equal to 2.5X. And it's going to be 40, but let me just belt and braces this. So X is equal to 40 millimeters, which is B. Okay. 19. So an uncharged capacitor is connected to a power supply which supplies a constant current of that. After that much time, the potential difference is this. What's the capacitance? Well, I know that Q equals CV. and Q equals IT. So 10 times 10 to the minus 6 times 100 times 10 to the minus 3 is the amount of charge, which is C times 5,000. And I can rearrange that for the capacitance and get 10 times 10 to the minus 6 times 100 milliseconds all over the 5,000 volts, which gives me that the capacitance is 2 times 10 to the minus 10 farads, which is A. Uh, 20 parallel plate capacitors connected across a battery. The energy stored is W. Well, the energy is a half CV squared. Okay, man, it's been a while since I've revised capacitors. Let me piece this together from first principles. I know that this battery, the energy stored is okay. Let me draw this out. Battery, capacitor, the energy stored is W. But that's because the battery that has a fixed voltage of V. So the energy is a half CV squared, which is equal to W. Now, I need to revise capacitors. I think that if the distance between the capacitor plates is halved, then the capacitance has doubled. That's what I think the syllabus point is here. Is there a way I can derive that? Probably. So let's consider... I'm just going to roll with that. Okay, good to know I need to revise that. And that's how you can use these past papers to do revision, right? It's because they contain all the topics. And the ones you feel resistance, that tells you, okay, hit the books, make sure you're completely confident on that. But what I think happens here is because it's connected... Oh, is it not just in the formula book? You see, exam technique. Why? You're right. Why am I struggling on this? Yeah. There we go. Thank you, sir. You're right. Exam technique. I should have gone to the formula book there. So we know that the capacitance is A epsilon naught epsilon R over D. So therefore, if D is halved, because they're inversely proportional, therefore C is doubled. And V is the same. So V squared will be the same. But at half, the new C times the new V is the same. So that's clearly just going to be 2W, which is C. See, this is why it is in the OCRs. Yes, it is in the formula book. It is 100% in the formula book. Okay, and that's again, another reason why it's good to have people here is because it pokes me to sort of demonstrate proper exam technique. I was struggling, so what should I have done? Should have gone straight to the formula book and see if it can do something for me. Okay, so parallel plate capacitor is made using, and you see now I'm going to the formula book because I think I'm still in ESAT mode where you have no formula book and you just got to know it. Sheet dielectric material in between in contact with two plates. The properties of 4 sheets of dielectric material are shown. Which sheet will produce the maximum capacitance? Well, again, capacitance is A epsilon naught epsilon R all over D. Parallel plate capacitor is made using a sheet of dielectric material between two plates. Okay. So in other words, A is going to be the same, epsilon naught is going to be the same, but we need to compare the relative permittivity over D. And now which one is going to have the biggest value of this? So let's compare. And we'll keep it in the same units. So 2 over 0.4 is 5. Let me make sure you can see. 3 over 0.9 is 3.3. 4 over 1 is 4. And 6 over 1.6 is 3.75. So therefore, A has the biggest value of epsilon naught over D, so it has the biggest capacitance, so the answer is A. Yeah, doing plenty fine on time. 22. Stores that much energy, discharges through that resistor. What's the maximum current? So energy, so 4.5 times 10 to the minus 3. That energy is a half of C V squared. So I can work out the voltage across it, which will be the maximum initial voltage. Now, if I run that 4.5 times 10 to the minus 3 times 2, hold on a minute, 10 to the minus 3. So multiply it by 2, divide it by 10 times 10 to the minus 6. You're going to get that V squared is 900, which means that V is 30 volts. So that initial voltage, which is the maximum voltage, is 30 volts. Now, remember, that is equal to IR. So the current is 30 over a resistance of 25, which is 1.2 amps, which is A. Nice. 23. The coil can rotate about that axis. The plane of the coil is at right angles to a uniform horizontal magnetic field of flux density B. Which statement is correct? Okay, let's think about this. Using my left-hand rule, when the field is acting in this direction, when the current is acting up, this force is acting in towards the axis of OO dash. And then here, when the current, yeah, so both those forces are acting towards the middle. So it's more of a squeezing action. Is that right? Equal in magnitude, opposite in direction. Oh, no, the vertical sides. Wait. That could be correct. Hold on. So field, current up, look, sort of, look. So I think that force acts in. I think that force acts in. So I think it's more of that. So I think that's in the plane. So I don't think that's a non-zero couple, because that's acting in the line of the axis that it's rotating in. So the perpendicular distance there is 0. So no couple. Let's think about, do no forces act on the horizontal sides? I don't think that's true, because fields, because I can easily, so the current would go that way, current field. So there the force is up. So in other words, all of these forces are acting towards the center. This force acts down, this force acts up. So it's not C. But then A looks like D. Am I getting something really wrong here? Okay, let me try and work my way through this. Because A and D look like they're kind of saying the same thing here. Because it's a square coil. I think I'm getting something wrong. So I'm going to make a note of this. Does D take into account gravity? Oh. I think that's getting really in the weeds. I think, maybe. So this one's tricky. So I'll make a note of question 23. I'm going to venture a guess. Well, we know it's not B. We know it's not C. I think it's more likely to be A than D. Oh, no. Got it. Okay, I know why it's not D. Yes. Because let's write this out. They don't act towards the center of the coil because here they are all purely the forces horizontal. And here it's all vertical. But you'll notice if this was always acting toward, that is fiendish. If it was always acting towards the center, these would be like at angles, and it would only be in the middle that the force is doing its like thing. As opposed to, so it would be this kind of situation, as opposed to the real situation where it's uniformly in one direction, where this direction is not towards the center. So that's why it's not D. That's why it's A. That's wild. Okay, but I got around that. 24. So this small rectangular coil falling between two magnetic poles. So it's cutting field lines, so there should be a voltage induced. What is the rate of change? So it's also the, hold on. Induced EMF is the rate of change of flux linkage. So when is... Okay, no, we can think about this differently. Let's think about this as... These have gotten harder, haven't they? I can't remember. There's a formula for this. Let me check the formula book just in case. Fields. No. So if this is moving through with a speed v, then it's the rate of change of flux linkage. Flux linkage is BAN. Rate of change is change in that over change in time. Now, dA dt for a small area, that is V times dt times L. So it is equal to B, it's Bivel. So Bivel, yeah, BVL is the rate of change of flux linkage, but it's not... I think here it is not that it's not changing at all because the magnetic field is constant in there. So the amount of field lines being captured by the coil stays constant there. So I think it's 0 in C. I think it's going to be D on account of that's where it's moving the fastest. As in this BLV. So that's what I think this is. Because it's falling, it's accelerating. And because it's accelerating at D, well, it's certainly D over B. So then is it A or is it D? I think it's D. I think it's D because that's where it's moving fastest. So I'm going to go for 24D, but these have definitely increased in difficulty, haven't they? 25. How am I doing on time? 15 minutes left. Alternating EMF is induced. Alternating EMF is induced in a coil rotating in a magnetic field. What is the phase difference between the maximum flux linkage and the EMF? Oh, between the magnetic flux linkage through the coil. Well, the EMF is the rate of change of flux linkage. So if it's rotating, then that would be like a sort of, that would be a differentiation. So voltage is rate of change of flux linkage. So if the flux linkage, for instance, was something of the form of sine omega t, then V would be of the form of cos omega t, and we know those have a phase difference of pi over 2 radians, so it should be C. 26. Induced EMF in the coil. So a field linking a coil. So it's rate of change of flux linkage. So here it is constantly negative. And here it is constantly positive but bigger. Oh, it's negative rate of change of flux linkage. I forgot about Lenz's law. So here it will be constant positive and then constant negative, which is more negative value, which is C. I can go through that in more detail later. Just want to make sure I get through with enough time. And then we can begin the marking. So 27. Coil P is connected with the cell in a switch. Closed coil Q is parallel to P and arranged in the same axis. Force acting on Q after the switch is closed. So the switch is closed. Current moves there. So current moving in a coil creates an electromagnet. This now has a changing magnetic field in it, which induces a back voltage, which induces a current, but only while it's changing. So it's definitely short-lived, because then once it's constant, it's not changing, you get nothing in there. And it opposes the change that creates it. So if that creates a north pole on the right side, this will create a north pole on the right side, and it will repel, and it will be acting to the right. So I think the answer is D. Won't be attractive. Okay. 28. Gamma radiation intensity is measured at a distance. Well, we know that the intensity should be inversely proportional to D squared. Because it's equals to the power over 4 pi D squared, which is the surface area of the sphere that it spreads out over. So D should be a straight line. 29. Number of parent nuclei is N at time T. Radioactive element has a half-life of T half. Rate of decay is proportional to N. That's exponential decay. That's how it works. A. The end. No further thought required. Mass difference on 30. How many questions do I have left? Oh, not many. Mass difference is, okay, so we know that the separated nucleons are going to have more mass. So the separated nucleons, that is going to be 3 protons and 4 neutrons minus the 7.01436. I'm just going to run that real quick. So 3 times 1.00728 plus 4 times 1.00867. I'm just going to serve a checkpoint. So just to show you, so these guys sum to 7.05652 U. So that's the mass of the separated nucleons. And we can see that the mass of the nucleus is a little bit less, 7.01436, giving a mass difference of 0.04216 U, which is B. And then 31. The mass of the fuel in a fission reactor decreases at that rate. Right, well, the mass defect is, well, okay, let's, the change in energy is mass defect c squared. Let's divide them both by t, delta t. Well, that is power. Which is 6 times 10 to the minus 6. That's per hour, though. Careful, careful, careful. So let's think about this. Because we want kilograms per second. So in 1 hour, so in 300, if in that many seconds, it's losing 6 times 10 to the minus 6 kilograms. How many kilograms is it losing in 1 second? Let's divide by 3,600. So in 1 second, we're losing 1.67 times 10 to the minus 9 kilograms. So therefore, the maximum power is that 1.67 times 10 to the minus 9 times 3 times 10 to the 8 squared. So this thing times 3 times 10 to the 8 squared is 150 megawatts, which is B. And you can't see that. 150 megawatts is B. Is there a huge amount of time for checking? Nope, 7.5 minutes. It's also noon and I've got somewhere to be, so let's get this marked up so I can finish. But in terms of checking, I'll maybe show that with a math paper where it's a bit easier. Well, no, the first thing you should check is to make sure you've answered every part of every question and you haven't accidentally missed anything. That is the number one thing to check, and that I will check now. So scrolling back up, this would obviously be much easier if I'd written in the paper itself, because you can just sort of see. So I have answered 1.1, 1.2, 1.3, 1.5, 1.6, all good. 2.1, 2.2, 2.3. Now, what I should also have done as I was going is to make sure before I move on that I've actually answered the question as asked. 5, 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, and then 5.1, 2, 3, 4, 5, 5.6, 6.1, 2, 3. Great. Then 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I'm seeing everything. Okay, so I've answered every part of every question. Not a huge amount of time. I'm going to stop the timer there, and let's go straight into the marking phase. I'm looking in particular for the wording of the descriptive questions, because I think that's historically where I've always been weakest, and I imagine that will be where I'm weakest today. But all of my mistakes will still be instructive to you, and so I think it's still worth it. So looking at a mark scheme, 28 degrees, yeah. Breaks and bonds, got break bonds. Crystalline to amorphous, so ordered to disordered, yeah. Do they accept ordered to disordered? Maybe not, but so the reason why I got that, if I go back to the top, remember what I said about parsing out the question. So I remember this question it was talking specifically about the energy and its role that it played, how the energy transferred changes the arrangement. Well, what the energy does is it breaks the bonds, which is how I managed to pick up that mark. Potential energy increases, kinetic energy constant, great. The mean kinetic energy increases. Which I'm not sure I articulated clearly enough. Because you can't just, because yes, the different particles have different kinetic energies because they have different speeds, but on average, they have increased. So I may not have picked up that one with exactly what I wrote. 1.5. So 370. Good. So that was all fine. 1.6. Gallium. Yeah. 2.1. Go through the motions, and I got that correct. 2.2. Do they have a different method? Not really. 2.6 times 10 to the 8. Good. 2.3, the mass is 8.5 times 10 to the 25. Good. 2.4, titanium. Good. 2.5. So it could not make it. But I've got that. They argued it differently. I got the first mark, certainly. Yeah, so I definitely compared these, but I compared them more as for how much energy would be required to get to 100 meters. I think that would be fine. Yes, this I definitely said. So I think that would have been fine. But again, some mark scheme analysis just to work out if you said the same thing. So magnetism is up. Electric is down. Good. 1.8, yep, 18,000, good. Rearranging that was totally fine. 3.4, 1.56, yep, that's in bounds. So just remembering that you had to double the radius to get the diameter of that semicircle. 3.5. 2.8 times 10 to the 5, perfect. 3.6. So you can see my calculation game is strong. Yeah, this is the one where it was asking, in fact, it was asking for a descriptor. I wrote a calculation, but I worked out that m is proportional to t squared. So the ions are given the same force. No, let's do work done. So the work done is the same, which so that's the same. So the smaller mass is given a greater speed in a smaller time interval. Okay, so they just wanted the qualitative explanation. Let me go back to the question there so you can see exactly what they had asked. So here, just for the qualitative one, because they have the same charge, they are given the same energy. And then because the masses are different, because that energy is a half mv squared, if the mass goes down, then the speed goes up, and so the time goes down. And you can then work it out. So yeah, the context clue that they wanted that more qualitative, it was more discussed, there wasn't room for equations, it was sort of multi-lines, that kind of idea. So in exam technique terms, that's how to get around that. 4.1, 10.6, 5, straight line at 10.6, I say horizontal line, 250 hertz. This I'm not convinced on, but is it? Oh yeah, 4 times 10 to the minus 4, perfect. Perfect. Reduce the time-based setting. Boom. Uncertainty is due to the smallness of the divisions, and this actually means the waveform stretches horizontally in the x direction, so it takes up more divisions, and there's less uncertainty in the time measured. Nailed it. Pleased with that. Oh, reject electrostatic. Is this not one of the fundamental forces? No! No! I forgot my wording. All right, so this again is why you've got to, like with the qualitative stuff in physics, just hit the book and know exactly how they want it worded. I just messed that up in my head. It's strong, weak, electromagnetic, and gravitational are the 4 fundamental. I thought it was electrostatic. Apologies. Got my wording wrong. Radially away from the center of the gold nucleus. So let me mark that actually. So that is definitely wrong. That should have been electromagnetic. Um, 5.3. And this is why. So I knew it, but again, this is why you do your mark scheme analysis, is just to hold yourself to the highest possible standard about how to explain it. 5.3. 5. What were they saying? List of justifications. Those deflect down. Can't be 4 as it would backscatter. Can't be those as the deflection would be too small. So I think I would get that for what I said. 5.4. I got 1.4 times 10 to the 7. 5.5. 5.7 times 10 to the 15. Nah, I didn't give any of those. I said they have the same density. What it is they have similar masses and similar volumes. Which is, in other words, the components of density are the same. Constant separation and are incompressible. Okay. Where again, this is, I'm not going to go into too much detail because this seemed to be an AQA specific topic, but again, for any of your specific topics, with all of the wordy ones, learn how they want it explained, adopt that, so the next time you see a similar question, you give them back the exact wording that they gave you. Um, 6.1. I wasn't confident on this. This absorbs a neutron if it's thermal, absorbs a slow-moving neutron. Uranium 238, I said deflect. They wanted scatters neutrons. That's what I mean about the wording, right? And then I said fission, but they wanted to explain splits. Yeah, no, uranium-238 is not involved in fission, but they wanted you to explain what fission is. They wanted you to explain that means it splits and gives out more neutrons. Let me look at any context clue that would have given me that, because that's usually the hardest part in a physics paper, is to work out what exactly they want from you. Okay, so I suppose the game I could have played here is to say, A fission event is examinable content, so explaining what a fission event is not the worst idea. So if I'm checking my work, by the way, in a real paper, I wouldn't have spent as much time explaining. I would have time to go back and check. And typically what I would have done in your position is do this, add more detail to my written explanations just to make sure I pick up everything they could have explained or they could have wanted explaining. So here I would have been like, okay, but let me demonstrate what a fission event is. Because that's examinable content. Let me just prove everything I understand from the syllabus. Rather than answer the question, use the question as an opportunity to demonstrate what you know from the syllabus. They only have one shot to like get a sense of what you know. You're like, well, I'm going to show you I learned this, and I'm going to show you I learned this as well. Look at like I didn't put in that work for nothing just for you to not ask for it. Let me explain to you what fission is, just so that you understand it. So in playing that game, I think is how I managed to do as well as I did. 6.2, 1.35 kilograms. Yep, it was to show that. So 3.7%, and that's valid. Remembering to include the plus 52 on the bottom as well. Although they did condone using that ratio, but it's not, strictly speaking, legit. Going through the multiple choice, it was D, A, C, D, C, D, B, D, C, D, A, B, A, C, A, D, C, C, D, D, A, B, B. Okay, so those were all correct. And I'm glad I did this, by the way, because they aren't giving explanations for their multiple choice. So let me go back through those and just see if anything in particular there requires further explanation. So it started from question 7, and let me find those in the question paper as well. So here, I don't think this requires further explanation, apart from the fact that there are multiple ways around a question like this. I like my before and after technique because I find it's more applicable to people with different understandings of the physics. But you do what you want to do. If you've developed a personal technique that works better for your brain, is a bit more efficient, you can use it consistently, then go for that. So I showed it 2 ways, sort of down here as well. Multiple variations. I think 7 the way I did it requires the least understanding. 8, I did a similar sort of before and after technique, comparing, but it's understanding what varies, right? So in order for there to be no net transfer, it means the pressures are the same. So we're really comparing the mole ratios to get the mass ratio. And again, a very similar technique on question 9. So I took some time at the start using the formula book to get this equation for the average kinetic energy of a particle, and then built that up to the total energy by multiplying by the number of particles, and then connecting that to moles like they wanted me to do. I could also realistically, I wonder actually if I missed a formula that I could have used, because I think no, I didn't miss a formula, but what I could have done is to recognize that K times Na is just R. So in other words, the total energy as well, I could have written as 3 over 2 nRT, which is obviously a lot more familiar. Honestly, a strat might be to make videos going through all the multiple choice questions from all the main exam boards. Just to get a little more traction here for the exams in May, June. That's not a bad idea. All the multiple choice questions from all the main exam boards. Yeah, because if we know there aren't proper mark schemes for them, I think that's a good idea. Because I'll need to do that. Okay, I will write that down. Because I think there is some benefit to having the long form questions explained to you, but you're right. If you've got a mark scheme, then that kind of already tells you what you're doing anyway. But I have a lot of people asking me for multiple choice, and now I understand it specifically because it doesn't explain the answer. It just gives you the answer. So that, good to know. I like that your head's in the strategic game. So that was how to do this. And again, I did it before and after on this. Well, really, in this case, I reformed the 3/2 KTNA, which was E, so it's 4/3 E. 10 was fairly straightforward if you just know that the volume is A cubed and use the formula given in your formula sheet. Again, 11 was straightforward. 12 was straightforward. It was just a definition. Been playing strategy games since you were like 7. Been quite good. It's fun. Strategy, it's like, it's honestly, it's really good when you start getting into like career development. That's when it's real fun. Oh, you're right. That is great advice for other people to learn from this. You're saying the reason why you're taking a gap year is because you, by your standards, flopped the A levels because you only started revising in May. This term is very important for revision, which is why I'm starting now. Wow. Wow. Okay, guys, this is a legit case study here. So this person in chat is saying the paper ones, the papers he did at the start of the season were like D's and C's, but the paper threes at the end of the seasons were A's and A stars because they were the ones at the end when you'd actually revised and were ready. So yeah, making sure you do your revision with plenty of time. I say once April hits, your knowledge base is kind of locked in. From April, it's all about exam technique. So this term is so, in fact, let's have this conversation. So don't revise 1 week before exams. Can confirm that is a sound piece of advice. But in terms of revision strategy, actually, while we're here, this term is so critical. So we're recording this now in like January 20th. This term moving through to April is where you kind of lock in your knowledge base. Because once you start to feel the exams creeping, there's this kind of stress where it's like, okay, what you've got is what you're going to use. And it's really difficult to build up, especially across all your A levels, all of that knowledge up all at once in a very short time frame. So you want to make sure that this term is spent revising stuff so you have less to do at the end. So bringing everything up to a sort of a level base so all of it can be raised up at the end through past paper revision all in one go. But you don't want to be relearning things past April. And this should hopefully be done in school as well, where you're learning all the content, sort of finishing that off fairly early, sort of in February, March time, but then really spending that time dipping into all of the topics and refreshing them all so they're kind of fresh at the front of the mind so that they can then all be refined at the end rather than relearned. But if I'll say to you, if you got A's, A stars in paper 3, that clearly shows the potential. And so revising with enough time now, going through like doing past papers and doing some good post-game analysis of your technique. So like from this, I know, oh, I need to revise capacitors because I wasn't 100% certain on that. So coming out of a paper and going, these are the points I need to revise further conceptually. This is how to execute better in terms of exam technique, learning the precise wording. That's all the stuff you can do to raise yourself up a level. 13 was fairly straightforward. 14 was fairly straightforward, as was 15, as long as you understand these relationships for the electric fields. The inverse square relationship for the field strength versus the inverse relationship for the potential, and then understand what that means for a distance of 3L. If you're someone who's not that good at proportionality, you could have done this using a before and after situation. So if you know that E is equal to KQ over R squared, then that means ER squared is constant. So E2 R2 squared equals E1 R1 squared. And R2 is 3R1. then that means 9e2r1 squared equals e1r1 squared, where the r1 squareds cancel and e2 is e1 over 9. So it's a bit longer, but this is what I mean. If you have a robust before and after strategy where you have something equal to a constant, and therefore that quantity is the same before and after, that can be used to always get through these. And you can have done exactly the same thing with v equals kq over r to say that vr is constant to get that it's v over 3. So that before and after strategy is very helpful in multiple choice. I liked how I handled this question. Because it's a point charge, we know it's a radial field, discounting A and B. And we know that the potential field lines get further spaced. Or rather, let's think about it. So the electric field strength is the potential gradient. These are fixed potentials. So as you can see, we know that it's strongest closest to the charge, which means that the potential gradient should be highest closest to the charge, which means you should be getting that. Let me explain what I'm saying. So on 16, another way we could have thought about this is to say that if the potential if the electric field strength is the negative of the potential gradient, well, these changes in V are fixed by the equipotential lines, steps of equal potential difference. So what we know is closer to the charge, where the E field is higher, this thing has to be higher, but the delta V is fixed. So the way to make this quantity bigger is to have delta R be smaller. That's why these delta R, these distances between the potential lines, is smaller closer to the charge, because E is bigger closer to the charge. Also a comment, Mattis Math has amazing math questions for math and further math, which you're using. Online Physics Tutor has hard A-level physics questions on all topics. You haven't found anything for chem yet. There's also obviously Save My Exams if you're willing to pay for that. But in terms of free resources, yeah, I think a lot of people have stuff that they like to use. There's obviously Math and Physics Tutor, Online Physics Tutor. You have, I really like, I'll show that at the end, actually, what I like to revise from. I'll just make sure I've got explanations for all of these first. 17 was fairly straightforward. 18 was fairly straightforward once you'd set it out properly, but I think I explained it okay the first time. 19 was fine. 20 was fine once I checked the formula sheet. So good exam technique, check the formula sheet if you're ever stuck. See if you can find a way out. 21 was fine. 22 was fine. 23 was so tricky to parse out. So they are all acting towards, they seem like they are, but that they're just not, because here it's vertical and this is vertically downwards, which is not towards the center. So once I clocked that, that's why it couldn't be D. Yeah, no, that was tricky. 24, I liked my explanation. I feel like we could have done better. It is true that in general, V equals B bivel, BLV, for a coil, rectangular coil moving through a magnetic field. And now V is increasing as it falls, so that will be, excuse me, biggest at D. That felt like a good explanation. And do you know what? I'm going to stick with it. 25 was fairly straightforward if you understand. For 24, hold on. Can we say it's when the most electric and magnetic fields intersect in a given time? What do you mean by E and magnetic fields? Because the rectangular coil shouldn't have an electric field going through it. It's really just about cutting the field lines. I really do think it's just to do with the speed and the rate of field lines being cut. So it's because it's moving fastest at D, the field lines are being cut the fastest, and therefore that's where the induced EMF will be a maximum. Wouldn't the field cause electrons to flow? If the coil was... If it was in a closed circuit, which I suppose in this case there's no guarantee that it is, but I doubt this involves talking about back EMF and electron... I think my explanation is simplest, but it doesn't mean your explanation is wrong. So if you've got the electric field, it's cutting the field line. There is an induced voltage, which is, let's say it's causing current flow. Then they would have current moving in a coil. That would create a magnetic field, certainly, but that wouldn't necessarily tell you about the induced EMF, though. That's more of a consequence after the fact, I think. So what happens after the EMF is induced is kind of irrelevant. So the fact that that then causes the current to flow, which then creates a magnetic field, is sort of a consequence, but that happens after the induced EMF. I don't think that then comes back and causes the EMF to be bigger. That would be my explanation. So we'll see. I'll come back and chat about that if we need to. 25, I think, was explanatory if you understand the sinusoidal nature of the induced EMF. So they differentiate. Sine and cos have a pi/2 phase difference. 26, I like how I explained that. 27, I like how I explained that. Because look at how I tied in different parts of the syllabus, by the way. So this was talking about, I mean, this isn't directly what this question is about, but it was the electromagnet. In fact, let me start annotating now on the thing. So here, the current flows. So let's say the current flows in such a way to make that the north pole of the electromagnet and the south pole. We know what's going to happen. The current is going to flow in Q's such as to make that a north pole and that a south pole, because Lenz's law says the direction of the current is to oppose the change that creates it. And so that will always cause repulsion. So this will be pushed to the right, but it will only be short-lived because it's only while this is changing. Once this is, because that's a cell, which is DC, once that's a steady state current, which is not changing, nothing changes. And so no force, no EMF is induced in Q, so no force is generated. 28. That was that was okay. This was okay. You just have to know that for exponential decay, because it's exponential, that means that the rate of decay is proportional to n. Where it's specifically, it's equal to lambda n. It is the decay constant times n. Gives you the number of particles that decay in that time period. This was fairly self-explanatory if you know the process for mass difference. 31 was fun. So it comes from E equals mc squared. Divide them both by delta t. So that E over t gives you power, which I had to convert into energy per second. But once I did, sorry, I had to convert that into mass loss per second. But once I did, that power, sorry, I shouldn't have written P equals that. That was irrelevant. But the once I converted to power equals this guy, the rate of mass loss times c squared, which gave me my 150 megawatts. So that one was quite fun. So definitely giving me an idea about how to make the best use of this live solve time. to give explanations for these multiple choice questions that people have difficulty with. The written explanations, we'll see how time efficient it is. It may be better for me to do, like you say, do multiple choice across the syllabuses because there's only a set number of weeks between now and exams. I think it's genuinely, y'all are done in like 20 weeks, which means I only have like 20 live solves left. So to get through the math syllabus and the physics syllabus, making sure there's explanations for all the multiple choice, that could be a good way to go just to make sure you guys have resources that you need. Right, so I think let's stop there. 2.5 hours in, that's about all of your attention that I think I need to take up in one day. But yeah, hopefully you found that useful in terms of the exam technique, moving through the paper. I obviously stopped to chat while I was doing this, so it means that I didn't have as much time to go back and check my work, but hopefully you find it sort of helpful anyway, especially these explanations in the multiple choice section. So we're going to leave it there. I will be doing a seminar series. I think I'm going to do it on connected particles, especially lift problems, which I find that students have. And again, that's sort of both in the math and the physics across syllabuses. So I think that's a good general place to start for the seminar series. Much shorter. I'm planning on doing that, I think, tomorrow evening. Let me just check my calendar real quick to make sure that is doable. Yes, so I should be doing it tomorrow at around 5 p.m. So I'll make sure to populate that stream in advance so people know it's coming. And I will see you if you can come to that tomorrow. So with that, I'll leave it with you. Work hard, have fun, and I'll see you guys next time. All right, take care. Thanks, bye-bye.